vertex. Well, I went to this, I took this edge first, and now this vertex is probably going to connect to here. Or if not, there's going to be something even closer. So this adjusts to the relative density of points and has some nice properties. It works in 2D really well. In higher D, then you kind of can think of these higher dimensional cones, and you kind of get this to work, but it's not quite as well understood. So this is another way of doing it. It has some nice properties. The third way is to build a structure called a well-separated pair decomposition. The definition is really technical, but it's some cool properties. And it's basically based on a quad tree decomposition of the space. Forget if I mentioned this, when we're doing the similarity search for kind of Euclidean data, a quad tree is the way that has kind of some of the coolest theoretical bounds. It doesn't work as well as some of these randomly shifted KD trees. But it's kind of a hierarchical space decomposition like a KD tree, but ensures that the kind of each cell is always kind of a square or a cube at different levels. And so if you do this, then you draw kind of one edge from each level of the hierarchy that you build. And this has really nice properties, and you can get it so even the degree of any edge is not too big. So there's this other quad tree base way of building these spanners. And this is very similar to things you may have heard in other fields called like the multifold method, or it's used as a key thing within like the fast-cast transform. And so this is kind of a very useful spatial decomposition, and it's very intimately related to these T-spanners as well. So I think I'm out of the time for the whole semester. Hopefully you enjoyed the course, and I'll see you Wednesday at the poster session.